This is Nick Oswald welcoming you to this bite-sized bio web seminar, which today is sponsored by Zeiss, the world's only one-stop manufacturer of light, X-ray and electron ion microscopy systems. Their extensive portfolio enables research and routine applications in the life and materials sciences. With Airyscan, Zeiss introduces a new revolutionary confocal imaging concept that will be presented in this webinar. The webinar is titled Zeiss LSM 880 with Airyscan, Revolutionize Your Confocal Imaging, and it's being presented by Chris Power, who's a 3D imaging specialist for Zeiss. Chris started as a product manager for both confocal and multiphoton laser scanning microscopy at Biorad in 2000, and in 2004 he moved to Zeiss in Jena to work for advanced development, where he contributed to the development of many new and exciting products in the area of optical sectioning, especially the light sheet microscope system LightSheet Z1 and significant advances in laser scanning microscopy. Recently, he moved back to the UK to be a 3D imaging specialist. Before we get started with Chris's presentation, just a little bit of housekeeping. As always, if you have any questions, please type them into the questions box, which appears on the right side of your screen. I'll put a few questions to Chris after the presentation, and we'll collate the rest of the questions for answering offline and email you all a document containing the answers at the end. So now, over to you, Chris, for the presentation.
Good afternoon, everybody. This afternoon it's my great pleasure to run through the new LSM 880 and to also cover the Airyscan. Confocal microscopy has evolved over the past 30 years from basic LSM 10 in the early days through many generations of system. And this workhorse of biological imaging has really evolved to the challenges of the applications. We tried to keep the system moving on to match the needs at the time. So over the past few years, as we've been working with the LSM 710 and 780, we of course have been continually asking people how to improve the system, what they would like to see in a future generation of laser scanning microscope. And the motivation for the 880 came from that feedback. Predominantly, whilst there were some requests for various features and tweaks on the system, the main feedback concentrated really on what people now know today as the cornerstones of confocal microscopy, that being speed, sensitivity, and resolution, albeit in Z or X and Y. And that kind of reassured us about the design of the 710 and 780 in some ways, in that there was nothing fundamentally wrong. It's just, as always, people want to challenge those cornerstones of confocal. And so as we moved into the 880 and also with the new Airyscan technology, we really wanted to push those three corners, those three aspects of imaging. This afternoon, I will take you through the changes in the 880 and how we've managed to bring better imaging, faster imaging, much more capability. How I'm going to do that? Well, first of all, I'm going to give, albeit an extremely brief, recap of laser scanning microscopy. I'll then run through some of the core improvements on the LSM 880. I'm then going to concentrate on the Airyscan, which is really the jewel in the crown of this stage of innovation. And then I'll wrap up and answer a few questions at the end. As far as the brief introduction, and I promise to keep it brief, really the heart of the confocal are the three things in the name. Laser scanning confocal, the laser scanning microscopy. And it all comes down to the laser being scanned through the system into the sample and then back in the conjugate plane through the confocal pinhole. And by doing this, we're able to reduce the out of focus light and collect an optical section. The optical section primarily and up to today being determined by numerical aperture, wavelength and pinhole. What that really means when you put it into practice is that light above and below is simply rejected. How that works compared to, say, wide field, well, in a wide field technique you might illuminate all of your specimens simultaneously and detect it all simultaneously. So you get an image instantly, or as long as the exposure time, but you have limited Z resolution because of the out of focus light. So in confocal, we scan a point at a time, we use that pinhole to reject the out of focus light, and we therefore suppress the haze and get a much better image quality, much better contrast. And that was really the motivation behind the original confocals. But over time, The number of techniques and the flexibility of confocal evolved from beyond just pure imaging. The machines evolved so that we could capture different regions and tiles. The flexibility that came from having a point scanner allowed us to do the photo manipulation techniques, predominantly associated with the F techniques such as fret and frap. The flexibility of having a single point scanner allowed us to look at molecular analysis. So these are techniques such as FCS, where you can park and look at the molecular diffusion in a very quick time domain. The monochromatic nature of the lasers in confocal and the tunability of the spectral range allowed very good spectral imaging. The flexibility of scan regimes allowed time-lapse imaging. The confocality itself allowed, of course, 3D imaging. And as of late, there are new techniques coming out with the point scanners such as RICS, numbers and brightness analysis, where we can drill even more information from our sample. But if I move on, I'd now like to talk about the actual improvements in the LSM 880. If I just show briefly a picture of the LSM 880, for those of you familiar with the LSM 710 and 780, the 880 at first glance looks very similar. The chassis has a few changes you can see different from the outside, but really in order to appreciate the changes we have to come inside the scan head and have a closer look. This is a representative beam path of one of the models of the LSM 880. If I walk you through the beam path, we couple the lasers in using two efficient beam paths here, one for the main visible wavelengths and one for the invisible wavelengths. The light, as it is scanned into the sample, now goes via temperature-controlled galvos. By that, I mean that they are water-cooled, and I'll come back to that in a little bit more detail later. The returning light, well, the excitation and the emission light go via what we call the twin gate. This is a very low incident angle dichroic system so that you get much greater levels of blocking than you do in previous generations of confocal. The light then passes through an apochromatic pinhole optic in order to provide the typical sectioning associated with confocal. And then usually we would then pass the light into what we call the QUASAR system. So this is a system where we can spread the light out spectrally, and in a single shot we can capture the entire spectrum. Compared to previous generations, we now also water cool this system here for a number of benefits. The first being that by water cooling the detectors, we can lower the noise floor and increase the sensitivity of the detection. And the second benefit is that by cooling the electronics, we have a much higher data throughput. So this means we can acquire more channels at faster frame rates. Finally, we have the Airyscan, which is an optional detection unit we can add on, which allows super resolution, but more of that a little bit later on. Coming back to the basic LSM 880, I mentioned that we water cooled the galvos. Why do we do that? Well, the main reason is galvos, when they move, they heat up. And beyond a certain movement, beyond a certain speed, they simply melt. So we have an absolute speed limit you can run in a point scanning confocal. Typically on the 710, 780, with a certain zoom field, let's say fully zoomed out, a zoom of 0.7, you might be able to image at a couple of frames a second at 512 by 512. On the LSM 880, because we now water cool the galvos, we can run 50% quicker. We can grab 3 frames a second. Also, this scaling applies at all different zoom factors. Of course, on a confocal, when you zoom, you can increase the speed, and therefore by zooming to higher zooms, we can now get faster speeds. So we can now, on the LSM 880, go up to, for instance, 13 frames per second at 512 by 512. And if we change the image format in Y, we can run much, much quicker. So this can be interesting if we want particularly dynamic studies of regions, and not just for pure imaging techniques, but also for correlation techniques such as RICS, or numbers and brightness analysis, where we may need to image the same region very, very quickly. The increase in the speed Of course, on earlier generations of system, we could scan at a certain frame rate. If that frame rate was sufficient, you could instead use the water cooling to offer a larger field of view. So for instance, if that was the field of view shown on the slide available on the LSM 780, you can now acquire a 4 times larger field of view on the LSM 880 at the same speed. So you can either basically go quicker or have a larger field of view compared to the previous generations. Now, all of this we maintain while still having a linear scanner. What is a linear scanner? Why does it matter? Simply put, as you move your point scanner across the pixels within your image, you have a certain pixel time or pixel dwell, the amount of time the light lingers on that pixel. Well, we at Zeiss feel it's very important to make sure that that is uniform across the scan line. So each and every pixel has the same amount of light on it. The second thing is we want a very good duty cycle. So this is the ratio of time spent scanning to time spent not scanning. Not scanning being when you turn around and get ready for the next line. When we were looking at scan techniques, there are ways in which you can scan using a sinusoidal scan. The downside of this is, first of all, you end up with non-linear pixel dwells, meaning the pixels at the edge of the field of view get exposed for a longer period than those in the middle. Now, there are ways to deal with it. You could keep a uniform pixel dwell, but this would skew the image. So most commonly, you either collect different amounts of light across the field of view, and therefore have brighter edges than the middle, or you discard the light at the edge. Another downside of the sinusoidal scan is the duty cycle is lower. You only have, say, 60% of your time scanning to 40% not scanning. So in order to acquire the same signal to noise as a linearized scan, you have to put in more power. Basically, we feel that linearized scanning really has no drawbacks. You either get higher signal to noise when you're looking at the same imaging speed and the same field, or we end up with longer pixel dwells, or for instance we can lower the light, the absolute light per unit time, in order to lower bleaching. A final point on this is if you enter into FRAP or some of the photo manipulation techniques, another huge advantage of the linear scan is that when you scan, you bleach at the same rate regardless of where you are in the field of view. Whereas in a sinusoidal system, as you can see in the image in the bottom right, as we scan across an image, we get non-linear bleaching. So it makes it very hard not only for routine imaging, but also for photo manipulation techniques. So that was the scanning of the LSM 880. This slide shows the detection possibilities of the LSM 880. The top-end model, we have 2 high-sensitivity multi-alkali detectors for the blue and the far red end, and we acquire everything in between on the 32-channel gallium arsenide array. The PMT options where we don't have the 32 array, we have either 3 standard multi-alkalis or 2 multi-alkalis and a gallium arsenide detector. So there are different options to kind of suit the demands and the requirements of your experiments. Another new feature of the LSM 880 is the experiment designer. So as systems have evolved to the point where they're basically over time people need to do more and more repetitions in order to get their data published. And what we've done with the experiment designer is we've tried to make an intuitive GUI so that you can design repetitive experiments with complicated experiment routines. So what the experiment designer allows is for you to plan complex experiments where you combine and repeat image acquisition tasks, and you can see all of this in a graphical element where you can track how you've set up these experiments. So in the GUI we have simply blocks, and you populate a block with settings, so your image settings, and then your multi-dimensional settings, so be it Z or T or tiling. And then you can create additional blocks with different settings for these. And in Experiment Designer, you can then set loops and repetitions of these. So for your multi-well experiments and complex experiments and loops that were previously just within the realms of programming macros, you can now do that intuitively within the GUI. Another thing I'd briefly like to mention is really the growing popularity of the clearing techniques. So clearing techniques have really gained strength since, as of late, the newer clearing techniques allow you to preserve fluorescent proteins. Scale has been one of the more popular techniques, and what I'm showing here is an XZ cut through of a 5.6 millimeter Z stack through mouse brain. In this case cleared with scale. These stacks are very impressive, but in order to get the most out of them you need a very high NA and a high working distance. And this is what we've now made available recently with the LD Plan Aprochromat 20x 1.0 NA lens. So this is a lens specifically designed for scale use with a correction collar, but primarily designed for a refractive index of 1.38 with a 5.6 millimeter working distance, and most importantly, not just corrected for, say, IR, but also for the entire visible range. Now, the clearing techniques tend to be slightly more favored in multiphoton. In the LSM 880, we've made a number of changes to improve the multiphoton aspect to push that sensitivity corner of demands that people were asking for. One such enhancement is we've updated what we call the BIG detector. So BIG standing for binary gasp. This is a very flexible detector that we either use for confocal imaging or for multiphoton imaging as a non-D-scan detector, where it can be used for FCS, FLIM, FCCS. So the detector itself can be used as an NDD either in reflection or transmission, as shown on this slide, or we can couple it onto the DC port on the back of the scan head. Here it can be used either for multiphoton or for visible imaging. I mentioned it could be used for FCS or FCCS because it's a very sensitive low noise detector. We also have now this FLIM output, so you can connect that to popular FLIM electronics boards in order to do lifetime imaging. Finally, the new design of this setup has removed fans from previous designs and now works entirely fanless, so there's no vibrations in here at all. Finally, with respect to improvements on the multiphoton, we have updated the nose piece for the Axio Examiner microscope, so we now have the option of 2 gallium arsenide PMTs completely integrated within the nose piece. So this will allow you to squeeze the absolute most out of the sensitivity when doing multiphoton imaging. That was a quick run through of the basic changes on the LSM 880. Now, with the LSM 880, we have also introduced a technology called Airyscan, and that's what I'd like to talk about today. The main reason and motivation for designing Airyscan came from looking at the beam path and looking at how we think about how confocal works. If I put up this slide again, which runs through the beam path of the LSM 880, as an instrument developer, you spend your whole time looking at this beam path, dreaming about this beam path, thinking, spending all your time thinking about how can we squeeze an extra few percent out of this and how to make it more sensitive. The problem is, over time, all of the easy challenges have been done, even all of the hard challenges have really been done on this light path. So as you're looking at this light path, you're kind of going, right, well, the galvos, how do we make them more sensitive? Well, we've changed the coatings so that now they're 99% sensitive. We can't do any better, apart from that 1%, but effectively they're as good as they can get. The narrow angle beam splitters are pretty much as good as they can get. The spectral separation, now that we have the recycling loop, so we use every photon we can in here, they're pretty much as good as they get. And then the detectors, we're using the top-end gallium arsenide detectors. So as far as today's technology goes, they're pretty much as good as they get. You kind of get to this point where you're going, now we have the 8th generation of Zeiss confocals. We think we're getting to the point of squeezing every last bit of sensitivity out of it. As we look at this, we also look back at how things have changed over time. So if I put up this graph shows the sensitivity of confocals going back 30 years to the MRC 500 and through various different systems over the age. And on the right of the graph, we see the LSM 880 when you use the multi-alkali detectors, or the LSM 880 with the gallium arsenide detectors. And this is a graph of sensitivity. The modeling depends upon the sample, but effectively you get an increase over the years. Now, if we think about the beam path and how we can improve it, we could actually model a system in the future which is as good as we can get. So I mean, if the galvos were not 99% efficient, but 100% efficient, and if every single component in that beam path is 100% efficient, how good can we possibly make a confocal in the future? And this is where we come to the concept of an ideal system. So really 100% quantum efficiency, 0% loss confocal. And that's represented by the bar on the right. What I really wanted to show with this graph is that compared to the first systems that came out and compared to where we can be, we're about halfway with the LSM 880. The remainder of the improvement and the difference left to come predominantly comes from the detector technology, and we're pushing that as hard as we can. So here we are in a situation going, are confocals pretty much getting to the point where they're as good as they can be without a huge jump forward? And this is where the LSM Airyscan comes in. All of these assumptions about the sensitivity of a confocal were based around one somewhat false assumption, which was that the pinhole is 100% sensitive. The pinhole is as good as it can be. And partly these assumptions come from the fact that the pinhole hasn't really evolved in the past 30 years so much. We've managed to get the newer generations so that the pinhole is a lot more accurate, it's a lot more reproducible, and it's very well aligned. But the pinhole still works as a hole that either lets light through or doesn't. The way the pinhole works has not changed in 30 years. And this is what we now want to do with the Airyscan. So how does it work? Well, the light is passed out of the output port from the LSM 880 through a filter wheel, through some zoom optics, and then it is imaged onto a 32-channel array. And what does this give you? Well, it predominantly gives you much better resolution. Initially, this will give you much better resolution in both X, Y, and Z. So here are some mitotic cells that we imaged in the University of York. This is the maximum intensity projection. On the next slide, this should be the Z stack playing through from bottom to top. The image on the left was captured using the gallium arsenide array internally to the LSM 780. The image on the right is an image captured using the Airyscan coupled to the same LSM 880. The next image is an XZ cut through of that data set, just to show the bottom image with the Airyscan has better axial resolution compared to that of the internal detector. Here we have some Muntjac cells with mitotracker red, and again we show the resolution increase of traditional confocal on the left compared to Airyscan on the right. And then finishing off for now, we have some fibroblasts showing the resolution increase, the sliver showing YZ improvement. And whilst not so exciting biologically, I think when you look at the resolution improvement on beads, it does stand out what a resolution improvement we can get from the Airyscan. Now, how does it work? The main idea behind the Airyscan is what can we get if we close the pinhole? It's no secret that by closing the pinhole, you can increase resolution. So here is an extract from the Jim Pauly handbook, kind of the Bible of modern day microscopy, where the confocal handbook says if you close down the pinhole, you can gain 40% resolution increase. However, why has that been ignored? The reason is that the signal level goes down by 95%, and this was too big a hurdle for biological imaging. And this is what we try and overcome with the Airyscan. The next few slides I'm going to show you come from what we call the Confocal Principles book. This is a PDF that we make available from Zeiss. There is a bit.ly link in the bottom right-hand corner to take you directly to the PDF. This document that we've published for decades now has a number of graphs which, when you look very closely at them, it reveals how we can squeeze more information out of the confocal. The first slide I present is basically the full width half maximum in Z versus pinhole diameter. This is what most people associate a confocal with. What it simply shows you is with a big pinhole in X, you get a big section. And therefore, by closing down the pinhole, you narrow your optical section. And this is why most people buy a confocal microscope. But the next slide shows the effect on resolution as you close down that pinhole. As you go from 1 area unit down towards 0 area units, so a completely closed pinhole, both the lateral and axial resolution of the microscope are improved, but at the cost of sensitivity. These next graphs from the handbook show how this trade-off of sensitivity and resolution really works. The left-hand graph shows a cut-through of 2 point spread objects. Now, for these objects to be resolved, as you image across them, the Gaussian, you need a dip between the two Gaussians. So this drop and dip is how you're able to resolve the two objects apart. Now what the graph shows you is when the area unit is 1, you get a certain dip and a certain resolving power. As you open the pinhole to say 2 area units, you don't really get an improvement in in lateral resolution anymore. So effectively, from an area unit of 1 up to bigger pinholes, your lateral resolution is the same. If, however, you close the pinhole, the drop between these 2 points gets deeper, so your contrast improves, and therefore your resolution improves. And this happens up to about 0.2 area units. So you can see here on the graph, from 0.25 area units to 0.05 area units, you no longer get an improvement of resolution. So that's the operating regime. From 1 area unit down to about 0.2, we can get a resolution improvement. However, the graph on the left is normalized, where each graph is normalized to itself. The graph on the right, all of the graphs are normalized to the 2 area unit graph. And what you see is, whilst you get a deeper dip in between these 2 point objects as you close the pinhole, you do it at the cost of most of your sensitivity. So eventually down here at 0.05 area units, you just can't see the signal at all. So this is why most people simply haven't done this in the past. So how to exploit that in a real system? First of all, I'll just show how a conventional confocal works. In this diagram, we show an excitation probe, shown as the purple dot here, and then a detection probe, so your 1 area unit detection, shown as the dashed line. And the graph in the middle is meant to show the point spread function of a molecule within your sample. Well, as you scan your both excitation and detection across this, you see your intensity increase and then decrease. And as you do that, you can map the PSF, you can work out what we call the full width half maximum, and you can see the resolution, which typically is about 240 nanometers with green light. With the Airyscan, I showed before that we don't have a single detector, we actually have 32 sub-elements. And typically when we use the system, we scan a slightly bigger area. So each of the elements shown as hexagons on the top left here, each of these 32 elements are about 0.2 area units each, but in combination they cover 1.25 area units in diameter. So what happens when you then scan with this system? Well, first of all, let's just pretend that we only scan with the central element of the Airyscan. If we do that and we map what just that single element sees, we see less signal by 95%, as the handbook predicts. But whilst we get less signal from that single element, the resolution of it is much smaller, again, as the handbook and the theory predicts. However, whilst we're scanning that single element, we're also acquiring all the other elements. So let's now look at what one of the other elements saw, in this case, a left-hand element. Here, as we scan across the molecule, the brightest intensity detected is actually when the laser spot co-aligns with the molecule and this element is detecting off-axis, and then the signal goes down again. If you map that and you look at what you're imaging, you see again a point spread function. Again, it is weaker, and again it is dimmer, but it is also offset. So how do we use this usefully? Well, we combine the data. So if we take that pixel we just acquired, or so that element of the array, which is offset, and then we take, say, the center pixel that I showed before, well, to combine the two data sets, we simply shift the curve we acquired at the edge, and then we add it to the signal we acquired in the middle. And by doing that, you get information from both of these elements. Now, that is with two elements. As we're scanning across, all 32 elements are mapped and recorded at the same time. So we can apply this image processing routine to all of the elements at the same time. So we acquire them all simultaneously, we map them all, and by doing that, when you look at the combined curves here, you get a tighter curve, so better resolution, and you get a taller curve, so better sensitivity. In addition, because we've got the individual information from each of the 32 elements, we can apply a deconvolution step where we use knowledge about where the scanning probe was relative to the detection in order to push the resolution down even further. So typically by about a value of 1.7, which means about 140 nanometers in the real world. Does it work? Well, we tried it, and luckily it does. So here is an image of beads where we show the resolution improvement. But beads are only fun for developers, so if we flick back to the real world, here are some images we acquired from the beta testing. This is telomere replication, and if we zoom in, again we have an image on the left acquired with the gallium arsenide array in the LSM 880, and on the right we have the image acquired with the Airyscan. And you can see that not only does the Airyscan improve resolution, but you also have much greater signal to noise. So the two things combine to get you images you just simply couldn't before. The Airyscan technique itself works with all common dyes. So in this case, this is an example of MDCK cells with prominin and tubulin markers. If you can image a dye with a normal point scanner, you can image it with the Airyscan. It's as simple as that. You don't need to think about the photo bleaching characteristics or the Stokes shift or any of the details of the dye. It's as simple as if you image it today, you can image it with the Airyscan. Multicolor imaging is made possible either by the filter wheel or by laser switching. So we have multiple bandpass filters, so you can quickly acquire 2, 3, 4 color images with the Airyscan. Because the detector in the Airyscan works just like, well, I wouldn't say just like any other detector, but because the rest of the imaging system is the same, you can do everything you would normally do on a point scanner. You can zoom into a region, you can change your laser wavelength, your orientation, and you can really just pick out the area you're interested in the sample and just acquire that. So the rest of the system just behaves as you would normally expect. A really nice part of the Airyscan is that you get these improvements regardless of the imaging lens you're using. So in this case, I show images acquired with a 10x magnification lens with the confocal versus the Airyscan. And if we look at the comparisons here, you see sensitivity improvements and contrast improvements that you just wouldn't see with the normal detector. To the extreme point, with a 20x 0.8 NA lens, with the Airyscan, we can get the kind of performance we would usually expect from a 63x 1.4 NA oil lens. That's the increase in sensitivity and resolution we expect. And all of this, as I said, you can do with typical imaging techniques. So in this case, we're looking at GFP expressed in Arabidopsis root. Here you have a single image taken on the left, a single image taken on the right with the Airyscan, and you see the increase in signal to noise. In typical samples like this, the increase we see is equivalent roughly to that you would get with an average of 4 normally. So imagine having an average of 4 without having to put in 4 times the laser power, without having to put in 4 times the time. So because of that, we can get these kind of stunning movies without bleaching the sample. Really, with the Airyscan technology, what we've done is we've found a way to overcome one of the bottlenecks in the confocal, which is really the pinhole, by squeezing more information both from within the Airy disk, but also from acquiring from a slightly wider area. And it's really going to let us do things over the next few years that we simply didn't dream we could before. In terms of use in the software, you can either use the Airyscan as a super resolution unit, in which case you get this improvement down to about 140 nanometers in X and Y and 400 in Z. Alternatively, you can use it in a virtual pinhole way, where we acquire a few different pinhole sizes simultaneously. So you could change your pinhole size after the acquisition, or we can run in a confocal mode where you just add everything together and it just behaves as if it's an extra channel in the system. And then in the software, you get an additional view type for Airy images where you can just click and see the kind of before and after the super resolution enhancement. So yes, just to wrap up then on the Airyscan, it really is a revolutionary approach that gives you a new detector that can function in different ways. You can either use it to push the resolution or the speed or the sensitivity, and it gives you images which I hope you'll have appreciated, give you SNR you just couldn't have had before. All of this happens as quick as you can move the point scanner. So now we have the cooled galvos. We can do many live cell experiments. The add-on unit is much more cost-effective than buying a dedicated super resolution system. So we're hoping this will make it a much more affordable and routine way of stepping into super resolution. It works with simple dies, your standard dies and protocols, and you can upgrade it. You can upgrade onto the LSM 880 from December and other systems later on. So just to kind of summarize and wrap up the presentation today, the LSM 880, we've really tried to push it so it's a system you can use for pretty much anything today. We've expanded it with options to improve multi-photon, and it's also still compatible with super resolution via the Alry system. We have new detector configurations available, and we have the water cooling for improved speed, lower noise, and improved data readout in the electronics. We do all of this using the fastest speed you can get from a linear scanner in confocal, and that's the best way if you want quantitative imaging, linear intensities across your image, and really superior imaging. We have tools for your complex experiments in Experiment Designer, and we have the new detectors for multi-photon and confocal. So the big two, the nose piece gallium arsenides, and of course the Airyscan. So really, just finishing with the Airyscan. With the Airyscan, you can get better results whatever you're doing. If you want more sensitivity with the Airyscan, you can collect light that would have either been discarded outside the mechanical pinhole. In addition, you can use the light that fell within one Airy unit more efficiently. So you just image much more sensitively with the Airyscan. Or you can use it to really push the boundaries of resolution. So typical gains of 1.7 in all 3 dimensions, which means a fifth of the size in your confocal volume. Or you can use the improvements in sensitivity to really push speed of. So for instance, as I mentioned before, you wouldn't need to average as you would have before. So any time you spent averaging can be gone. Or you can use combinations of these. The customers who've used this today have been impressed. A couple of quotes from Dr. Peter O'Toole. This was a disruptive, a real innovation. And Ian Morrison said this was something he really hadn't seen before. That concludes my talk. There are a few links here if you'd like to find a bit more information. So either zeiss.com/880 for the main product information, zeiss.com/Airyscan for information directly about the Airyscan unit, and the bit.ly link at the bottom is the Confocal Principles book that I showed some graphs from today. I have time for a few questions.
Thank you very much, Chris. That was a really excellent presentation of an amazing concept. Chris, we have a few questions. We can just dive right into those if you're ready for that.
Yeah, sure. Go for them.
Okay. When stating a 1.5-fold increase of resolution, what are you comparing that to? What does that compare to?
1.7 is the resolution improvement we typically expect you to get when you compare a confocal image taken at one Airy unit compared to one taken on the Airyscan. We say 1.7, this is really what you would expect to get both laterally and axially on a normal sample without having to push things, I should say. Just taking a normal sample you use day to day.
Guys, we're just going to have a few questions here. There's questions coming in. You can keep answering them. As I mentioned earlier, we'll answer those. Zeiss will answer those offline. Probably managed to fit in a few more here. The second one is Airy scanning a proprietary Zeiss technology?
Yes, it is. The idea of using light which fell on the pinhole and light that was within the pinhole has been something of a kind of dream for years and years and years. I'll be honest, I work, even in companies I worked with before Bio-Rad and going back to the year dot, people have tried to do this.
Okay.
What we've done with the Airyscan, though, we've done it both in a combination of you need a very, very accurate beam path, and you need very good knowledge of how this works, and you need a very unique detector behind that. So technologically, we have a few unique things, and I'm sure there's some IP in there as well.
Okay, sounds complicated. Okay, so what happens to the actual pinhole when you're using the Airyscans? It seems like it's no longer needed.
Yes and no. The pinhole itself, yeah, it is kind of no longer needed when you use the Airyscan. What happens to it physically is it opens up to allow light through to the Airyscan, but we keep it at a size where it still helps to reject some of the out of focus light coming through. But at least for a basic explanation, you open it up and ignore it. And
so how does the Airyscan compare to the existing Zeiss Alry super resolution systems?
The Alry super resolution systems come in both the PALM, so the localization, and then the SIM, so structured illumination. The PALM really maintains the best resolution, albeit on thinner samples. The Airyscan is quite similar to and will be compared to the structured illumination systems. Simply put, however, if you want to push the resolution on a conventional sample, structured illumination will let you routinely day-to-day get a 2-fold increase, whereas the Airyscan routinely day-to-day will give you about a 1.7 increase. So Alry, slightly better resolution. It's also going to be quicker for bigger fields, and arguably for some samples it could be more sensitive. I say arguably, you could argue that the Airyscan on some samples may be more sensitive. It's going to be a long-running debate here. So the Airyscan, however, compared to the Alry, the main benefits are you can bolt it to an existing confocal very easily. So if you're buying a normal confocal anyway, it's a less expensive add-on. It will be faster for small regions, and also it's going to be much better at punching deep. Kind of previous super resolution systems struggle beyond 10 or 20 microns. With the Airyscan, we've gone up to 50 microns.
The last question we have time for, I guess you've kind of partially answered that there, and that is, can Airyscan be upgraded to previous Zeiss microscopes.
Yes,
Light scanning
yeah, so we can add the Airyscan onto LSM 710s and 780s. There are some provisions, but almost all of them it will work, and we just really need to do a component test. So if you talk to your local specialist, they'll be able to tell you what needs to be done. But yeah, if you've got a 710 or 780, the Airyscan is for you.
So I guess that's all the questions that we have time for at the moment. They're still pouring in. As I mentioned, Zeiss will answer the rest of your questions offline and we'll publish the answers for everyone. If you still have a question, just please put it into the questions box there and it will be answered, or if you think of something later, you can email it to me by replying to your webinar invitation and I will pass that on. So that just leaves me, Chris, to thank you for a very illuminating presentation and a good discussion.
Okay, thank you.
And thank you to our sponsors, again, Zeiss. And please don't forget to visit www.zeiss.com/LSM880 and request an instrument demonstration. And finally, thanks to you, the audience, for taking time to attend and listen in. If you've enjoyed the seminar and you'd like to view the video recording of the session, please visit the webinars page on bitesizebio.com. It should be available there within the next 24 hours, and we'll also send you an email reminder to let you know that it is there. And there you can see the other webinars that we have lined up for you in Bitesize Bio's Webinar Festival. And so, until next time, good luck in your research and goodbye from all of us at Zeiss and Bitesize Bio.